Today I will show you how you can leverage your data as future insights. At Calculators and Discovery Tools team, we started a project to contribute to drug discovery by developing a machine learning module, and our goal is to provide high accuracy, reliability, and confidence at scale. The workflow starts with collecting the data that can originate from public sources like PubChem or Campbell or your in-house data store. The trainer engine is responsible for standardizing chemistry, generating descriptors, providing you the most important features for feature selection. Throughout configuration, you can tune the hyperparameters, then validate the models, and for the final model, you can also achieve error bounds using conformal prediction framework, and you can assess the performance of the generated set of models. In our analysis, you can plot various accuracy metrics and compare your models head-to-head, or drill down and see the predicted values, observed values for your test set. When you have made your decision on which model to be used, Trainer Engine also offers a RESTful API endpoint for integration, and it can run batch prediction as well. Today's challenge is related to parallel artificial membrane permeability assay profiling if you have a permeability problem. The collected dataset was standardized, and we have filtered the molecules to fit into the 0-800 Dalton range, and the permeability was classified into a low and high class using 100 threshold value of the phenotype field in the original dataset. First, we expanded this and enriched the dataset with descriptors using chemical terms, and we generated the high-quality physical-chemical descriptors available from the ChemAxon portfolio, including log-P, log-D, pK, or solubility, but also included combined scores like MPO or geometry-related properties like fraction of sp3, ring properties. We extended these descriptors with fingerprints and the max key and the k-nearest neighbor based descriptor. We are building a random forest model, and we also spent time on optimizing the parameters. But the first step is the feature extraction to be able to know which properties are correlating with the measured activity. And I'm showing you the descriptors with their importance values calculated from the individual decision trees in the random forest. And as you can see, the lipophilicity related properties that are colored with blue are the most important ones, the log-D at a given pH. But the second cluster, what we have identified, is related to pK, and some of the descriptors like MPO or solubility also depends on these two. So what we have learned from the dataset is that lipophilicity and pK are the two properties that can be controlled during design. In the model optimization, we have used this information, and the most important descriptors were used as a configuration to generate further models, and I'm showing you the number of features that are included versus the accuracy expressed as the Matthews correlation coefficient. As you can see, this reaches a plateau at 20. So we have selected these 20 chemical terms defined descriptors, and this best model had 0.57 Matthews correlation coefficient on the test set that had 406 cases and 0.81 SN accuracy. So from the total available descriptors, we shrink it down to a smaller set of descriptors, and then looked at the dataset again using a clustering method, Jarvis-Patrick. You can see here the number of molecules in a given cluster versus the cluster ID, and the largest cluster had 86 cases. And to be able to have a scaffold-based split, we analyzed this dataset and used the scaffold from it as a substructure search to enrich this selected set further. And finally, we had 128 test set molecules, and the rest was used as a training set. And the highest animative similarity in between the test set and the training set was found to be 0.83. So now we are building a model for a completely new chemotype using the past information. And this is the selected cluster that is classified as the test set and that doesn't have a representative in the training set. And after further optimization, we identified 21 descriptors and obtained a model with 0.45 Matthews correlation coefficient and 0.73 as accuracy. So to summarize, during training, we identified the most important contributing features. We named ionization and lipophilicity as being the most important parameters that can be controlled. With random splits, we achieved high accuracy with 81%, and with scaffold splits, we also generated a meaningful model for novel molecules. After selecting this model, this can be integrated into your design environment, and this can be used for prospective predictions in Design Hub or in our Playground interface. But Trainer Engine also offers batch calculation using an SD file. So with that, I want to thank you for your attention.